This is a heat transfer problem, and we are working with a computer setup where we have this enclosed box and it has 5 circuit boards inside it. Now we also know that we have a fan that pushes air through this box and it comes out on the other side. We know that the power consumption of this fan is 35 watts. We know that the inlet temperature is 20 degrees Celsius. We know that the difference between the inlet and outlet cannot be more than 15 degrees Celsius. So from this we can find that our outlet temperature is 35. Now we have it given that our convection coefficient is 180 watts per meter square Kelvin, and we also have the density and the specific heat of the air given. Oh, one more thing. We know that each of these circuit boards is dissipating 20 watts of heat. Now they want us to find the minimum volumetric flow rate for the air that needs to be pushed through this computer in order for our, right here, this one, to be correct. We need to make sure that this temperature limit is not exceeded. So what kind of volumetric flow rate will we need for the air? And for part B, they want us to find the surface temperature of one of the components. Okay, so we're gonna use energy balance for this, for solving this problem. And I'm gonna tell you right now what is the energy balance written onto. So what is our control volume, so to say. So we're gonna be using this enclosed box, but our control volume is the air inside it. So from here all the way here, just the air, not the box. The fan is not included in our control volume. It's an exterior device that's putting 35 watts into our control device, a control volume, and also the board itself. They are not in our control volume, just the air, and these boards are putting 20 watts into our air, the control volume. Okay, so just to be clear, our control volume for our energy balance will be just the air itself inside this computer. Now I'm gonna kind of describe, well, all of each of us have their own way of figuring things out, but I'm gonna describe to you how did I got to the conclusion that I'm gonna need energy balance for this problem, because it's quite a complicated one. So how did I realize that, oh, I need energy balance for this? So since we need a volumetric flow rate, right, what kind of formula can I see this in? So for me, density is mass over volume, and the same thing is mass flow over volume flow, right? So I know that I can see this guy in this formula. So from here, density I have given. So if I think of mass flow rate, where did we see this one? Well, in our energy equations, we always had internal energy and the other kinds of energy, and we know that we have these two differences. This is in thermodynamics, right? We have the capital marcation and the lowercase marcation. So the difference between them is exactly the mass flow rate. So for example, here you're gonna need these equations in our calculation. I'm just showing you ahead how did the mental process go. So we have internal energy, and the unit for this one is just watts, right? And this one is mass flow times blah blah blah. Now if we divide this by mass flow, then we have the lowercase version where there's no more mass flow in it, and our units become watts per kilograms, and the rest stays. Now where do we have these, the internal energy and all the other ones? Well, in our energy balance. So that's how I ended up thinking that I'm gonna need the energy balance. So now let's break this out and we'll see where these appear in it. Now let's expand our energy balance out. We have the energy in, energy out, energy generated, and energy stored. Now for each energy in and out, we know that its components are heat, work, and mass flow, right? So we have the in and out. Now energy generated stays as is. Now here in the stored, what do we have? We have change between internal energy, kinetic energy, and potential energy. Now let's cross out everything that we do not need. So, do we have our air heated in one way or another? Well, to take a step back, our energy generation, okay, that is what we're gonna consider this 20 watts that's coming in. This will be generation. So since we have 5 times 5 boards, that's 100 watts, and this will come into right here. So we're not crossing that one out. But any other kind of heating do we have, or cooling? We do not. So we can cross these two out. Work in. This fan is putting work into our control volume, so we are keeping it. We have mass flow, the air that's coming in, flowing in and flowing out. So our mass flow in and out must stay. Now, do we have any work out from this system? We do not, so we can cross it out. Now on this side, what kind of changes do we have? Is there any kinetic or potential energy changes? No. We are only changing our temperature, right? So that is internal energy. And if you can see right here, this is the expanded version of our energy balance. And this is where my mind was going, that I'm gonna need this when I was thinking of this. Now, let's continue. Here it is, everything written down simply. What we had left, everything crossed out. Now we can expand these two guys, the mass flow, which is the mass flow rate times enthalpy, and in and out for both of them. Now for enthalpy, right here, we know this formula, so we can go ahead and plug that one in. There it is. I factored out our mass flow. Now here we can cross some stuff out again. These ones fall out. The pressure times volume, that will be the same on both ends. We can cross them out. Everything else stays. Now, here I just rewrote it as it comes from up here, but then one step lower, I factored out the negative and moved it on this side. So now it looks like this. Now, small u minus small u out minus in, this is our delta u, the small one, right? And so we can go ahead and plug this one into right here. Here we have it, and go ahead, solve for our mass flow. Here it is. Now if we look at it, we know this one, we know this one, we know this one, T2 we know, T1 we know. The only thing we don't know is our mass flow. But that's not what they are asking for. They're asking for volume flow. So let's go ahead and use our very first formula that we thought of, this one. Now I'm going to solve for mass flow right here, volumetric flow times the density, plug it in right here. Now I have it solved for volumetric flow, everything we know here, so we can go ahead and plug in. There it is, and after a little bit of number crunching, we can find our volumetric, wow, I couldn't say it, flow rate right there, 0.0077 meter cube per second. That's what we needed. Okay, now let's focus on the second question. We need to find the surface temperature for one of the components that would be placed on these circuit board, any of them, and where they are asking us to tell or figure out where would we place this item that we want the surface temperature, they tell us that this component has a very high temperature sensitivity. So that means we want to make sure that in no chance gets overheated. We wanted to place it somewhere in this box in a location where it gets the best chance of being cooled. They also tell us that the heat flux on the surface of it is 1 watt per centimeter squared. Now, how do we approach this? Take a look at it. We said that the temperature coming in is at 20 degrees Celsius, and as it passes through this system, on the other side, it will be coming out with a temperature of 35, right? So, if we want the best cooling, that would be on this side where the air is still the freshest, so to say, still at 20, not at the highest of 35. And also, since this is a convection situation, our convection is always the strongest right here at the beginning, not at the end. Okay, so our component would be placed on any of these boards, but here close to this edge where T is 20 degrees Celsius. Okay, now as we said, we have a convection situation. Let's go ahead and convert our flux that they gave us, which is 1 watt per centimeter square. We can't use it this way, so let's convert it to meter squared. So that will be 10,000 watts per meter squared. So analyzing our convection flux formula, we can see that the flux we have right here, we have H given. Now Ts and minus T infinite. Which one is which? Ts would be the surface temperature that we're looking for. That's the component surface temperature. Now T infinite is the air that's flowing around it, right? So we said we're coming close to the entrance, so we're gonna use 20 degrees Celsius. So T infinite is equal to T in equals 20 degrees Celsius. There you go. From this one, we solve for Ts. There's the formula for it. Now we know everything. We can go ahead and plug it in. And there it is, 75.56 degrees Celsius is the surface temperature of that component. Now, just if you're curious, see, if you would place this component not here, but on this side, which is close to the exit, that is a temperature of T infinite would be T out, right? 35. So redo this calculation with 35 and you'll see that you will get a surface temperature for our component that is higher than this.